Okay, let's look at problem 18 on page 53, okay? So it's like basically what this problem does is this problem involves is each system is an echelon form. So it gives you lots of examples of echelon form systems. By the way, if you have a 0 equals 0 row, it's supposed to be at the bottom. So I think this one actually isn't quite an echelon form, but it's hard to tell because if you have something like this, okay. So say whether each system has no solution, one solution, or an infinite number of solutions. We're not solving it. We're just, so for each one, you could write down 1, 0, 1, or infinity. So why don't you take a moment and say, try to do A, B, C, and D. And then when you're finished, raise your hand, either a Zoom hand or a real hand. Well, I guess if you're not present, then a real hand wouldn't help much. And if you're not sure how to detect what's going on, then you can ask about it to sort of verify what's going on. Excuse me? 18 is number 18 on page 53. And first, just do, we'll do all of them, but just do the first 4. And then raise your hand, or if you're here when you're done, or if you're online, you can raise your Zoom hand. So you guys, we have one person that claimed, okay, I have 2 people that have done the first 4, and you also, and how about, okay, we've got 4 people, 5 people. Oh, and okay. So now you can check whether your answer is the same as mine, and I'll explain as I go along. So 18A, you have, okay, good, we're still, okay, messed up the recording a little bit there, but that's okay. This first system here, what you first want to do is detect leading and free. Both variables are leading, so it has one solution, and there's no contradictions, so you have one solution. This one has 3 variables, 2 of them are leading, 1 is free, so it's going to have an infinite number of solutions. This one has 3 variables, 2 are leading, 1 is free, so it has an infinite number of solutions. This just means that one of the equations originally was redundant, didn't give you, it had the same information that was in the first 2. And that's going to be an important concept. We'll see later why that occurs and what's going on. This system has no solution because it has a contradiction. The problem is, no matter what I choose for X and Y to make this first equation true, 0 is never equal to 4. So that's a false. So that's what happens if there's no solution. You get a contradiction. So there's 0 solutions here. Okay, how about the next 4? Do those and see what. We'll take a few minutes and then I'll go over them. Okay, we've got one person done. Okay, we've got two people who have answers. Three people. Just the next four, E through H. Okay. Well, I think we've got about most of the class. Let's look at number E. What do you think? Is that there's no contradiction, so it's either one or infinity. What do you think it is? Anyone want to hazard a guess? Excuse me? Infinite, yes. You can see even though Z is a constant, usually you've had like the first two variables be leading and the last one free, but here the first one is leading, the third variable is leading, but the middle one Y is free because it's not leading in any row. So you have a free variable, so you have an infinite number of solutions. And then you can probably see you have an infinite number here in F, in G, you have a contradiction, so there's no solutions. And in H, you have a free variable Y, so you have an infinite number of solutions. And you can probably see right away that I is going to have a contradiction as well as a redundancy, so it has no solutions. And what about J? What do you think for J? One solution, infinite. Yeah. What do you think? One? Infinite? One, yeah. Okay, so some people in class have thought one. I guess you guys, if you look, X, Y, and Z are leading, no free variable, so it's one solution. Okay, so this just gives you flavor that you can actually tell a lot from just the echelon form of the system what's going on. We only have, let me see, we have 15 minutes left. What I want to do is give you a preview of, let's see. We started messing around at the beginning of class with chapter 0, and the material that we've talked about here has all been in this section 2, solving linear systems. But there's a little bit here on this second piece here, which is making Gauss's method easier. Now, this introduces matrices to make Gauss's. It's a way of doing Gauss's method to make it easier. Now, to be clear, you can't use this on the first assignment. Okay. So you're just going to do equations. You're not going to use the easier way. You can do it the hard way, so to speak. Okay, now but let me first show you how to translate Gauss's method to make it clerically easier. Okay, so what we're going to do is we're going to introduce the idea of a matrix. Now, a vector was something like this: 1, 2, and 3. Okay, we can also have arrays of sort of two-dimensional array. For example, here 1, 2, 3, 4. It's an array of ordered numbers where you have rows and columns. It's like a double ordering. You know, you can either think of this as like a list of rows or a list of columns or some kind of two-dimensional array. So we're going to use capital letters for matrices. But then we have to be able to give name. These things inside the matrices are called entries. So 1 is an entry, 2 is an entry, 3 is an entry, 4 is an entry. And we need a way to say where those entries are. So we do is we number the columns and number the rows. And maybe I shouldn't use a 2 by 2. Let me use a 1, 2, 3, 4, 5, 6. Here's a matrix B, and here is column 1, column 2, column 3, row 1, row 2. And what we're going to do is we're going to use a lowercase b as a name for these entries, and we're going to use the row index and the column index to indicate which one. So the first one's the row. So this is going to be row 2. column 3. So it's always like like in one of those ancient Roman temple, you have Roman columns, right? You had columns in the temple. So you always think it's a Roman column, so the row comes first. That's all. This is always the row, and this is always the column. So B23, row 2, column 3 equals 6. B23 is a name for this entry. Okay, it's just an index notation.
What if there's like 11 rows? And what would you do then? Would you do like
Well, yeah, the thing is this,
11 and
that if you had 10, if you had 10 or 11 rows, then you would need to do like B11, comma 23, right? But since who wants to deal with matrix arrays that this would be in a linear system that had at least 11 equations and 23 variables. Well, we're not going to be dealing with that unless we're dealing with it on a computer. So to keep so some people out of purity want to put a comma in here. But if I look at this so I'm not reading this as B23, I'm reading as B23. Now, some people like to put 2, 3 here, but these commas then just appear everywhere and end up being that they sort of visually are more, once you get used to this, some people just can't get over seeing this as B23, or you want to read this as B2, sort of in your mind 3. Okay, Shruti.
If you put a giant array, and like, I don't know, like 23 rows, 23 columns, then you would kind of have to put the comma, right?
Yes, you would have to put the comma because you wouldn't know, but then you're probably going to be dealing with on a computer.
Okay.
And so what you do within a computer, you have a fixed syntax for arrays of arrays or matrices in which you are going to use commas. And so but then that's going to be a symbolic form. So here it's just a convention I'm using for this, that by convention, all of our matrices are going to be less than 9 by 9, So, I mean, basically we're rarely get above, well, some matrices will be larger. Okay. Yep. New page after. Okay. Here we have this idea of matrices. Now we can use this as a notation for, so let's say 2x plus 4y equals 7. 3x plus 5y equals 8. Here's a linear system. Now, what we're going to do is we're going to write this in terms of a matrix. We're going to write this as 2, 3. See, there's the 2 and the 3. 4, 5. And because these have variable, this is the x column, the y column, because this one's special, we're going to put a vertical bar here and then put the 7 and 8. And this is called an augmented matrix. It's called augmented because this matrix here, 2, 4, 3, 5, is the matrix of coefficients of the linear combination. Coefficients is the name for matrix. It's a hard word to spell. Matrix of coefficients. So coefficient is the number that's before a term in a variable in the linear combination. So this is the matrix of the coefficients in the linear combination. So if I started from this as a matrix, this matrix, the augmented matrix, augments the coefficient matrix with the 7 and 8. So we just call this an augmented matrix. Okay, it's got the vertical bar here, 7 and 8. Oh, and what we'll try to do in licks, here's the crucial thing. Well, I won't do that because we're not going to deal with this until later. So since you can't use this for the first assignment, it'll be a ways time before you can use this. And okay, so now once you have this, we can solve. This is just a notation at this point for this linear system. But here's how we can use it to do Gauss's method. Okay. We can do row operations the same way that we do these operations, because if you notice the row operation, the x's, the pluses, the y's, the equal sign just carried over. They never moved. They were always in the same places. So it's just this is just a simplification. We don't have to write the x, the y, the plus, the equal sign, but we're going to do row operations the same way with the same notation. But here I'm going to do, to avoid fractions, I'm going to do 3 row 1 and 2 row 2. And so I'm going to multiply the first row by 3. 2 times 3 is 6. 3 times 4 is 12. 3 sevens is 21. 2 threes is 6. 2 fives is 10. 2 eights is 16. So if I translate this back, it would be a different linear system, but it would I would translate it back by saying 6x plus 12y equals 21 and 6x plus 10y equals 16. But it's a lot easier to do these arithmetic maneuvers without all the clutter of the x's and y's. Then I can do minus row 1 plus row 2. And I get 6, 12, 21, 0, because minus 6 plus 6 is 0. Minus 12 plus 10 is minus 2. And minus 21 plus 16 is 5. And then I can see, well, it's an echelon form. The same way. Each column has zeros under it. So this is the second. Okay, so this is the x column, the y column. So both variables are leading. Now, you have to, we can translate this back to equations. The second equation here is minus 2y equals 5. Okay, there's not a contradiction. You're not saying minus 2 equals 5. It's minus 2y. So therefore, y equals minus 5/2. Then the first equation is 6x plus 12y, which is minus 5/2 equals 16. And then that's going to become 6x plus minus 30, right? Because 12 over 2 is 6. 6 times 5 is 30. Equals 16. And then 6x equals 16 plus 30 equals 46. And x equals 46 over 6. And we can at least get rid of the 2 to be 23 over 3. So the answer to this system is S equals 23/3 over minus 5/2. Okay, so now if I had not done this little maneuver here of this here, I would have had to do like minus 3/2 to kill the 3 here, but then I'd be multiplying minus 3/2 times 4 and minus 3/2 times 7, and there'd be fractions all over the place. If I had 3 variables, it could be a big mess. So this is a little trick. You get the numbers are okay, Catherine?
I think it's supposed to be a -5 because you did -21 minus.
Oh, okay. So we've got minus. Yes, I made a mistake here. Yes, and that's the other point. That let's say you did this and I didn't recognize. Let's say this has an error in it, but I've just gone through and I haven't recognized. So what you want to do is go back to this original equation. Let me see if I can bring up another. Let me 2x plus 4y equals 7, 3x plus 5y equals 8. Okay, so what I can do with this wrong answer is I can plug this back in, right? And say the second one and say, well, this is 3 times 23 thirds plus 5 times minus 5 halves equals 8. And I'm going to get 23 plus minus 25 times a half equals 8. Well, you notice that this is an integer, this is an integer, but this is a fraction, right? So if I bring this over here, there's no way this can ever, so this is a contradiction, right? So that means that, so it's not such a big deal to make a mistake, but it is a big deal to not check your answers by going back and plugging them in to the equation. Now, if you have an infinite number of solutions, you can't do that with everything. So you can only do it with a few values, but at least you should choose a few values to catch whether you've made an arithmetic error, because then you can go back and find, like Catherine pointed out to me, that I had subtracted 21 from 6 and gotten 5 when I should have gotten minus 5, which means that this is a plus sign and this is a plus sign. So this is a plus sign. And so this is going to be I hope this is going to be right. It's going to be, oh, this is a 6. What am I doing? Okay, like this is 16 minus 30, which equals like maybe minus 14. And then I'm going to get this x will equal minus 14 over 6, maybe, and then x will equal 7 over 3. That actually looks a lot better. Okay, so then I can come over and check whether or not 3 times 7.
I think we negative, negative 7.
Yeah, there's a minus sign here. I'm making errors right and left, right? Okay, so 3 times minus 7 thirds plus 5 times minus 5 halves equals 8. Let's see. Oh, so I still have a problem, right? So even despite that, there's some error in here that I've made, maybe. Right? Because I don't think I'm going to get an integer here and a fraction here. So there's some other error that I've made in here. Okay?
Professor, I have a question.
Yeah, Catherine.
Why do you do 6x plus 12 times 5 over 2 equals 16? Like, why do you do equals 16 instead of equals 21, maybe?
I'm sorry, where point my attention to
So like after you like made the matrix, you go back to like the equation, right? You put it back into like an equation.
okay.
So it would be like 6x plus 12 times 5 over 2 equals 21, or would it be 16?
Okay. So you're saying this matrix was wrong.
I don't know. I'm just
Okay,
asking.
let's look and see. 3 times row 1 is 6, 12, 21. This would be 6, 10, 16. And then I'm subtracting. This should be minus 2. This should be minus 5, right?
Right. And then if you scroll down a little bit, you use back substitution to solve for x. So then you have 6x plus 12 times
Here's the error.
Yeah.
Yeah, there's the error there. I was going so quickly, I used the 16 here, which should be 21, right? Yeah. Okay, so then we can see this is also one indication that sometimes these are easier in, okay, 21. Then we're going to have 21 minus 30. This keeps getting smaller and smaller, which is, I guess, good. Minus 9. And then we have x equals minus 9/6, which equals minus 3/2. So it's minus 5/2 and 3/2. And that's going to look a little bit better if I have 3 and minus 3/2 plus 5 times minus 5/2 equals 8, because this is going to be minus 9/2 plus minus 25/2 equals 8. If I multiply it through, it's going to be minus 9 minus 25 equals, again, maybe there's some other error too, because I've got a minus sign here, but an 8 over here.
I think the 5/2 is positive,
Excuse me?
is the 5/2 is positive.
Ah, the 5/2 should be here positive. So I'm all that, oh yeah, the 5/2 here is what? Oh yes, because it changed the sign. So there, so I'm multiple. Okay, so 5, do it here, 5/2 here equals 8 times 2. So we have 25 minus 9 equals 16. And that looks actually right. Okay, so we only have 2 minutes left. Let me show you on, there's a program on VeriVirtual that you have available, and you can also install it locally, in which you can, say, solve linear system, and you can have, say, 2 equations, and then we can put in 2 star x plus 4 star y equals 7. And 3 star x plus 5 star y equals 8. And we have the variables x comma y. We click OK, and then it says that this solution is minus 3/2 and y equals plus 5/2, right? So that confirms this is right. Okay. So let's say you're solving a linear system. You can check that your answer is correct. Okay. Then you can go back and find the errors, with more or less, maybe hopefully with more efficiency than I was doing up here. So this is on VeriVirtual. You can also go and find it. There's like lots of linear algebra things online. I'm not sure which one's the best one, that you can go and it'll do things like this, solve for linear systems. So that way you can sort of, like, what you present, there's no reason to have wrong answers. The only time you couldn't take advantage of this is when you hadn't left enough time for the assignment and you were just racing to get it done at the last minute, so you want to avoid that, so you can actually go through and get the right answer, and then the only points you lose will be on how to do it. Oh, and we have, I guess, coming into the next class, right? Okay, well, thanks for reminding me, though. We do have a scripting class coming in at 1 o'clock, so I should probably let you. It is 12:50, so the class is more or less over. Any questions?